Okay, so welcome back. The plan for today is to finish up section 5.1, complete section 5.2, and then at least get a good start on 5.3, or maybe complete it. So we're working our way through what's basically a review of operations on polynomials at this point. So we are going somewhat quickly through this material, but again, this is hopefully material that you've seen, ideally in the recent past, or at least at some point in the past in kind of an elementary algebra course that's the prereq for this. So that's why we're going a little more quickly through this material. But of course, if you have questions on any of this material, definitely stop me. I'm happy to go a little bit slower here or there if we have questions on particular topics or particular problems, or where did this or that result come from. The quote of the day for today is from my favorite professor in college, one of my graduate school professors, Dr. Bill Layton. So down at Pitt, he's retired now. And he would say, good decisions come with experience. And how do you get experience? Well, experience comes from making bad decisions. So I think these are good words of wisdom. If you do something, and whether it's in your academic career or in life more generally, and it kind of doesn't pan out the way that you would have liked, um, you can kind of, be sad and move on and forget about it. Or you can say, okay, well, is there a lesson I can take from that? Even if it wasn't entirely your fault that it turned out that way, there's often still a lesson that can be learned. So, we can take bad experiences or bad outcomes and not learn from them, or we can leverage that. We can say, okay, that's a sunk cost, as we might call it in finance. But what can I gain from that, right? What can I learn from that? But I think it's also there are many versions of this quote, but it's also good to think that we can learn from other people's mistakes as well, whether they're people that we personally know or just examples that we see in the news or online or something, letting other people suffer the pain, so to speak, whether literally or metaphorically, of making bad decisions and seeing how that outcome affected them and analyzing that. One example of this that I've been kind of thinking about lately as I chose this quote for these last couple of days. Um, my wife and I do rock climbing. We do rock climbing at an indoor gym, so we're not, super outdoorsy or wanting to go like hiking through the woods to mountains and things like that. And we definitely don't do that crazy stuff like Alex Honnold does with no ropes or any of that. But there's a channel on YouTube, and he does climbing fails, he calls it. And the whole purpose of this series of videos on his channel is he takes maybe 3 or 4 submissions from viewers of his, of recordings of people climbing that where something bad happened, that they never like die or really really get injured, but something less than ideal. Maybe they fall longer than they should have on the rope before the rope catches them, and it was more dangerous than it should have been, something like that. And looking at their mistakes, he analyzes them and says, okay, what could they have done differently so that if we're in that situation in the future, maybe we think, oh, okay, I remember that idea and I can do that differently in the future. So, especially with us being in the information age, being able to learn from other people's mistakes is hugely valuable. Um, but I think that's the quote of the day for today. All right, so moving on then to chapter 5. We discussed some semantics last time, some basic definitions of things, monomial, binomial, polynomial, things like that. We have this idea of like terms in polynomials. And remember that a polynomial is something maybe like 3x to the fourth plus 5x squared minus 1, something like that. It's a sum or difference of, I suppose, one or more terms. A monomial is just kind of like a degenerate polynomial, where each term is made up of a coefficient times a variable or variables to some powers. We talked about the degree of a polynomial and so on. So I have variable to power, x to the fourth in this case. So this 3x to the fourth would be one term, 5x squared would be another term, and maybe 1 or maybe -1, we would consider the third term, depending on whether we want to think of this as plus a -1 or just as -1. So those would be our terms. What does it mean to have like terms? Well, two terms are like terms if they have the same variable or variables. We could have something like, 2xy minus x squared y. That would be a polynomial as well. It just has more than one variable in it. Same variable or variables to the same power or powers. And this is, of course, respectively. So, if we have plus xy squared, none of these three terms are like terms. They all have the same variables, x and y, but the first term has x to the first and y to the first. The second term has x squared, so second power on x, first power on y. The third term has the second power on y and the first power on x, so they would not be like terms either. If we have two terms that are like terms, say 2xy squared plus 3xy squared, these have the same variables xy to the same respective powers, x to the first, y to the second. Well, this is just like saying, we have 2 apples plus 3 apples, or 2 oranges plus 3 oranges. We have 2 lots of xy squared plus 3 lots of xy squared. We can simplify this. We get a simplified term that is of the same type. It's of the xy squared type. It's an apple or a number of apples or number of oranges. And we just add the coefficients. 2 plus 3 gives me 5. I mean, I add the coefficients because I have a plus here. I do whatever operation is associated with those coefficients. So if I had a minus between the two terms, I would subtract the coefficients. Okay, so if I look at an example like this, 7y cubed plus plus 3y cubed, I see that I have two terms, one there and one there, that are connected by a plus sign. I note that both of my terms have the same variable y to the same power, the third power. So I can combine them together as one like term. And the new coefficient is just going to be 7 plus 3 or 10. Right? Once you get used to doing this, it's really trivial to go through and make these simplifications. But at first, there are a couple of things you need to check. You need to be comfortable picking out what are the different terms in the first place, right? It's kind of a jumble of symbols at this point, and you could pluck off the 3 or pluck off the x squared or something by accident, but the 3x is one term, the x or maybe the negative x is another term, and the 4x squared is a third term. So these are our three terms. And then we evaluate each of our terms to see if it's a like term, if it can be combined with any other term. I noticed that the 3x and the x are like terms. They have the same variable x to the same power 1. And the 4x squared is not a like term with anything else in here. Well, so the 4x squared just kind of comes over by itself. It can't combine with anything else. It just is what it is. But the 3x minus x, we're going to end up with a like term of the x type, of the x to the first power type. And our coefficient is going to be 3 minus 1. Remember, x, there's always kind of a hidden coefficient of 1 in there. 3 minus 1 is 2, and that's a positive. So this simplifies to 4x squared plus 2x, or 2x plus 4x squared would be the same thing. I tend to write my polynomials with the highest degree term first and then the next highest degree term, and then the next highest degree term, and so on. If I had a big polynomial like this where I had, you know, a bigger polynomial than this where I had 5 or 6 or 7 terms, I might even take one extra step and go through and just rewrite it so that so the terms are in decreasing order of degree. That's going to kind of put all of the like terms next to one another and make it easier for me to pick them out. So if I wanted to do that here, I don't think this is a complicated enough problem to warrant doing that, but just to show an example, I could rewrite this as 7k cubed. Cubed is the third power is the highest degree I see anywhere. Plus 5k minus 2k. I'll check them off as I go along, make sure that I got all of my terms. I did. I see that 7k cubed, there are no other k cubeds. So it doesn't have any other like terms to combine with. But the 5k minus 2k, those are like terms. They can combine to make a 3k. They both have the same variable k to the same power 1. So I know I'm going to end up with a like term as the result. And the coefficient is going to be 5 minus 2, or 3. Any questions so far? One thing we want to be really careful about with operations on polynomials is being super careful about all of our basic arithmetic and basic algebra operations. If I have something like this, I have one polynomial minus another whole polynomial, I've got to be really careful. I've got to make sure I distribute this minus. Really what I'd be doing is doing, plus -1 times, and then distributing the factor of -1. Maybe more technically speaking, that's what I'm doing, but we'd often just refer to that as distributing the minus. Kind of practically speaking, that's what we're doing. Now, this first polynomial, there's no real reason to have these parentheses here. We can just get rid of those parentheses. But the second polynomial's parentheses are very important. It tells us we have to distribute the negative to the 7x squared as well as to the -3. So I get minus 7x squared plus 3. Super easy to miss out that last little bit there, switching that last sign on the 3. And now again, I go and look through here for like terms. My highest degree terms are second power. And I do see that I have 2 of those. So I'm going to end up with some x squareds. And I have -2 minus 7, -9x squared. That takes care of my second power terms. Maybe I'll switch colors here so we can keep track of things. I see I have an x to the first power term. Do I have any others? No, it doesn't look like I have any others. No like terms to match with that one. So that one just comes down as is. And then I have 2 constant terms. Constant terms are like terms with one another as well, of course, just -1 plus 3, that's just plus 2. We can have an example like this one where we have, again, a distributive property to take care of first, but here we have a couple of different variables in play. So let's distribute, get rid of all these parentheses, and then search for like terms. And this second parentheses really isn't doing much because I've just got a plus sign there, nothing really to distribute through. And now as I look through, I see I have some common powers like n squared and m squared, but they have different variables. So I have to be careful to not think that those are like terms. They have different variables, even though the power is the same. But if I look through, one thing that I might do is ask, what's the highest power I see anywhere? 3 on the 2m cubed. Do I see any other third powers anywhere? No, because there's no other third powers anywhere, I know there's going to be no like terms for this one to match with. What's the next highest power I see? 2. Here I have to be careful because I have some n squareds, but I also have an m squared. Hopefully you can tell the difference in how I'm pronouncing that. I'm trying to be a little more explicit about n versus m. So for my n squareds, I know those are like terms. They can combine together. But I actually have 2n squared minus 2n squared. This would be like plus 0n squared. And instead of actually writing plus 0n squared, I would just not write anything. I probably would just go ahead and cancel them out like this. Just noting that that plus 2n squared, the minus 2n squared, they just go away. They annihilate one another. But the negative 5m squared, or the minus 5m squared, does come down. It doesn't have any like terms to combine with. We just carry it down. I have some m to the first powers. Negative 6m plus 1m is negative 5m. And I think that's taking care of all of my terms in my original expression, or I guess my intermediate expression here. And this is what I ended up with. I have no more like terms. There's nothing else I can combine together because even though each of these terms has the variable m, the powers are 3, 2, and 1, all different powers, no like terms. Then one last example in this section. So again, let's take care here. We have a lot going on in this problem. We have a 6 that needs to distribute. We have this negative that needs to distribute as well. The 6 distributing is, we're not too likely to miss that, but the negative distributing, easy one to miss. We also have different variables, m and n, to different powers. So we got a lot going on here, but let's take it one step at a time. We'll start by distributing the 6. And then we'll distribute the negative. Making sure that we distribute to both of those terms, switching both of their signs. And now we can go through and look for like terms. I have an m cubed. I don't have anything else cubed, so I know that there's no like term. For this, it can't combine with anything. I have an n squared and an m squared, but no other squareds. Those are not like terms because even though they have the same power, they have different variables. There are no other squares, so there are no other kind of candidate-like terms for either one of these two. These just come down as well. And then lastly, I have this kind of cross term, as we sometimes call it, m times n. We see m to the first, n to the first, and I actually do see a like term for that one. Here's another m times n. So I'm going to end up with an m n term. And I start with negative 12, and then I subtract 3, I have negative 15 mn. So not a whole lot of simplification there, but we did get two like terms that we were able to combine down to one. Any questions on any of this? So again, I think this is a pretty straightforward idea once you get comfortable and proficient at, number one, recognizing what the terms are. That's the first thing to be careful about. What is a term? And then the second thing is recognizing like terms. It's kind of a pattern recognition thing. the first 3 or 5 times you do it, it's a little bit tough. You have to maybe look back at the definition or be super careful, or maybe make a silly mistake once or twice. Problems 5 through 10 are going to go a little easier. And by the time you get to problem 20 or something that you've worked through, then it'll be pretty smooth. Okay, so moving on to 5.2 then. Properties of exponents and scientific notation. We have two properties of exponents to start with, the product and the quotient property. The product property x to the m times x to the n equals x to the m plus n. Remember that an exponent just means repeated multiplication. So I just have x multiplied by itself m times, and I'm multiplying that by x multiplied by itself n times. But if I just smash all these multiplications together, that's dot, 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 not a minus. Then I just have x multiplied by itself m plus n times. That's where this product property comes from. And the quotient property, pretty similar. If instead of multiplying by n, if I had divided by n, by x to the n, sorry, then I would like have n cancellations of x with x is in the numerator. So I'd have m minus n, x is left over in the numerator. And if I had more x's in the denominator, well, that's not a problem. We just think of that as like a negative exponent. Our negative exponent property, x to the negative n power, is 1 over x to the n. And our zero exponent property, anything to the 0 power, is 1. Right, if I have x cubed over x cubed, that's x to the 3 minus 3, that's x to the 0 by our quotient property. But of course, x cubed over x cubed is just 1. It's just the same thing over itself. We might want to include the restriction that a not be 0 here. That's maybe a topic that's outside of the scope of this course, but if we wanted to really be careful, we'd say a not equal to 0. And of course, x can't be 0 here or here for obvious reasons, because we have factors of x clearly in the denominator in those cases. But whether we should define 0 to the 0 as 1 or treat it as something like an indeterminate form that we're not really sure, that we're saying we're not sure how to treat this, we don't want to give it a definition, is maybe a topic for a different course. We also have the power property, x to the a power, that raised to the b power. Well, what does that mean? That means I take x to the a and multiply it by itself, b times. But each of these x to the a's is just x multiplied by itself a times. So this is like x multiplied by itself a times, and then x multiplied by itself a more times, and x multiplied by itself a more times, and so on. A total of b times, or that's just a times b copies of x multiplied by itself. So even though these properties look pretty esoteric, it's like, where did these come from? We really can see just writing out the multiplications. I think it's pretty clear to see where these come from. So if you're ever confused, wait, if I have, base to a power times the same base to a different power or the same power, is that like, do I add the powers or do I multiply the powers in that situation? I don't remember. We'll just go off to the side and write it out, either with an explicit example, like x squared times x cubed, and see what you get. Or you can write it out more generally like this. And product to a power property, x times y to the m, this is just saying take x times y multiply it by itself m times. But I know multiplication is commutative. I can just push all the x's to the left and all the y's to the right. So I just have m copies of x multiplied by itself at the beginning and m copies of y at the end. So we can split it up this way, right? Exponentiation distributes over multiplication. If we think of PEMDAS, the distributive idea, the idea of a distributive property, takes us one level down on PEMDAS. So multiplication and division distribute over addition and subtraction. That's our kind of usual distributive property. But the concept of a distributive property is more general, and we do have exponentiation that distributes over multiplication in this way. I had a debate one time a few years ago with an older math professor about whether that technically counts as a distributive property, and it definitely does. I showed him the resource. I'm like, this is what a distributive property is. It's not just the distributive property that everybody talks about. It's a much more general concept, the idea of having a distributive property. So this exponentiation distributes over multiplication. It's a special type of distributive property. It's, I think, right distributive and not left distributive, but just remember that distributive property takes us one level on PEMDAS. It does not take us two levels. So like x plus y squared is not x squared plus y squared, as we will see in just a minute here. Okay. Maybe not a minute, maybe 10 minutes or 15 minutes. Okay, so let's just work through some examples. And you probably it's probably good to drill these alongside with me, alongside me as I'm going through them. This is material that for a lot of you is going to be dusting off the cobwebs kind of material. If it's not, that's perfectly okay. If you haven't seen these in a while or completely forgot them or haven't seen this material at all in the past that you remember, it's going to take a little bit more drilling and a little bit more time to get acclimated to it, but I think it's still not too hard to get off the ground on this material. Okay, so I have 3y squared times y cubed. Well, this is just 3 times y squared times y cubed, right? And I know that I have my product property. I have the same base to an exponent multiplied by itself. So base to exponent multiplied by same base to exponent. In total, I have 5 copies of y that are multiplied together. 2 copies of y multiplied together times 3 more copies. And the 3 just comes along for the ride. Okay, what about this one? So 2x squared times 3x cubed squared. Well, here I want to follow PEMDAS. I do my exponent before I do multiplication. So I just bring down my 2x squared times, and then 3x cubed squared, that's 3 times x cubed squared. Well, that's 3 squared times x cubed squared. That was our product to a power property that we applied there. 3 squared is just the number 9. And then x cubed squared, our power to a power property, x to the 3 times 2, or x to the 6th. So this was just scratch work over here to the side. So that second original factor, 3x cubed all squared, that simplifies down to 9x to the 6th. And now I have a product of 2 monomials. I can multiply them together. 9 times 2 is 18. Multiplication is commutative. I can just put my numeric factors all out in front. And then x squared times x to the 6th is x to the 2 plus 6, or x to the 8th. Okay, looking at this one, we have a couple different variables here. We have m, and we also have n. I do notice that I just have two monomials multiplied together. No powers or anything affecting the order of operations here. So I have a -2 times 3 for my constant parts, my constant factors. That's -6. For the m's, I have m cubed times m squared. And my product property says that's m to the 2 plus 3 or to the 5th power. And then lastly, I just have this last factor of n. It has nothing to combine with, so that's what we're left with. -6 m to the 5th times n. Okay, what about this problem? This one has a lot going on, but the steps are very similar to the ones we've already done. There's just more steps, and we just have to be a little more careful about each step, but the steps are similar. We do have a product of two factors here, but each factor has an exponent. So I want to simplify each factor first. I want to get rid of the exponents, at least this outside exponent first. And then I can worry about multiplying the two monomials together. So let's start with 1/2 x squared y cubed to the 6th power. Well, I see that this is the product of three things to a power. And I can pretty clearly see that my power property is going to generalize. If I had x times y times z to the m, that's just m copies of x times y times z all multiplied together. I can put all of the x's first, all of the z's last, and keep the y's in the middle. And they're just going to recombine as x to the m times y to the m times z to the m. So I think it's pretty clear to see that this generalizes to as many factors on the inside as I want. I can distribute to a bunch of factors, or I can distribute this 6 power to the 1/2 to the x squared and to the y cubed. Did I get all my powers correct there? Yeah. When I'm writing and talking at the same time, I usually end up writing what I'm saying or about to say rather than what I'm actually planning to write. Wonder if that's like the same part of your brain or something that handles that, both writing and talking. Okay, for this first one, 1/2 to the 6th, I could multiply 1/2 by itself a bunch of times, or I could use my quotient property. This is 1 to the 6th over 2 to the 6th. And then I have my power to a power property that I'm going to use twice here. So times x squared to the 6th is x to the 2 times 6, or x to the 12th. And then times y to the 18th, y to the 3 times 6. And the only thing left to do is simplify 1 to the 6th over 2 to the 6th. Well, 1 to the 6th is just 1 over, well, 2, 4, 8, 16, 32, 64. So that's what my first factor here is. And then what's my second factor? Well, my second factor, maybe I'll do this one in blue over here, 4xy to the 5th. Or again, this is just going to be 4 to the 5th times x to the 5th times y to the 5th. Same idea, we can generalize this product to a power property to situations where we have more than two factors on the inside. So I have 4 to the 5th, x to the 5th, y to the 5th. I kept this as 4 to the 5th and instead of trying to figure out what that is, because I noticed that some of the factors of 4 are going to cancel with the 64 in the bottom. So if I put all my numbers out in front, I have 4 to the 5th power over, well, 64 is 16 times 4, or that's 4 squared times 4, that's 4 cubed. You can think of it that way, right? 2 to the 6th I can think of as 4 cubed. So that takes care of my numerical factors. My factors of x, I have x to the 12th times x to the 5th. I add the powers. X to the 17th power, 12 plus 5, 17. And then for my y factors, I have y to the 18th times y to the 5th. My product property says I add the powers, 18 plus 5, the 23rd power. Oh, not quite done yet. 4 to the 5th over 4 cubed. Well, I have a property that helps me with that as well. My quotient property, 4 to the 5th over 4 cubed is 4 to the 5 minus 3, or 4 squared. That's 4 squared equals 16. All of this boils down to just 16 x to the 17th, y to the 23rd power. Any questions so far? Okay, let's look at simplifying x cubed times x to the negative 5th in two ways. One using the product rule, and the other using the properties of negative exponents. If I use the product rule, x cubed times x to the negative 5th is x to the 3 plus negative 5, or x to the negative 2. Another way to think of it is I have x cubed times x to the negative 5th is over x to the positive 5th. I can move my variable over the fraction line if I negate the power. But 3 of these factors of x in the numerator are going to cancel with 3 of the factors in the denominator, leaving me with 2 in the denominator left over. But of course, 1 over x squared is just exactly what we mean when we say x to the negative 2 power. So we see these two do get us the same result as we would hope. Okay, if I want to simplify x to the negative 2 power, all raised to the 4th power, what would that look like? Well, the power being a negative power doesn't affect our properties at all. This is just x to the power negative 2 times 4, or x to the negative 8. If I have 4 copies of x to the minus 2, or 4 copies of 1 over x squared, we can see this is going to be 1 over x squared to the 4th, or 1 over x to the 8th, which is, of course, just x to the negative 8. What about a problem like this? In problems like this, we're suspecting there's going to be a lot of cancellation. Some stuff is going to divide out. There's also going to be a lot of stuff that combines together. So it looks complicated right now, but it should simplify pretty nicely for us. One thing that we didn't talk about really is our negative exponent property, x to the negative n equals 1 over x to the n. Well, but if I have a fraction, if I combine the negative exponent property with just some basic understanding of fractions from prerequisite material, if I have a over b to the negative n, that's equal to b over a to the positive n. Why is that? Well, I get 1 over a over b to the negative n. That's 1 over a to the negative n over b to the negative n. But then if I'm dividing by a fraction, I multiply by the reciprocal. So I just multiply 1 by the reciprocal of that fraction and pull that factor of n back out. So that negative power really just says kind of flip the fraction. In other words, x over 1 gets flipped to 1 over x, but 1 to the n is just 1. So we just write it as 1. So the negative exponent property really is more general than it would seem at first. So if I look at something like this, I could, distribute the negative 2 power into the numerator and denominator, but I could also just get rid of that negative power right off the bat by flipping the fraction. And now use my quotient property, my power to power properties, and so on. So my quotient property, and then my power to power property, I'm going to use twice. Y cubed to the second power is y to the 3 times 2, or 6th. X squared to the second power is x to the 2 times 2, or x to the 4th, times x cubed y. Let's write this as one fraction. This is y to the 6th times x cubed times y. We can see that this is going to be the way this works out, right? That this is the numerator because this is just over 1. So if that wasn't clear to you, why that x cubed y can just pop up top. We think of x cubed y as the same as x cubed y divided by 1, and then we're just multiplying two fractions, multiply the numerators, and we multiply the denominators. We just get x to the 4th times 1 is x to the 4th. The y to the 6th times y bit combines to make a y to the 7th, and the x cubed in the numerator divides out 3 of the factors of x in the denominator, leaving us with a single factor of x left over in the denominator. So definitely a lot of steps. We have to keep track of all of our properties, what properties we're using where. There would, you could definitely take a different approach to here. You could, to the solution of this problem, you could choose to not get rid of the negative exponent here and just deal with the negative exponent, just distribute through, and then use product property and so on to handle that negative exponent, at least for the one in the numerator. That would be fine as well. Right, x to the negative 4 times x to the positive 3 would give x to the negative 4 plus 3, x to the minus 1 in the numerator, which is what we see over here. So there are a couple of different ways to approach this problem. I tend to like to get rid of negative exponents if I can. It's just, I feel like a little less error prone for me. If I don't have negative exponents floating around, I'm a little less likely to make a silly mistake like, messing up whether that factor is in the numerator or denominator, something like that. Okay, let's look at another example here. So we have 3 expressions that, if we're not being careful, might look like they all represent the same thing, but it turns out these all represent different things. So let's simplify each of these, writing them with positive exponents, and let's do it carefully. So let's start with the first one, negative 3x to the negative 2. Well, here we have negative 3 times x to the negative 2. That's the implied operation is times. The negative 3, nothing is really happening to it. We do exponents before multiplication. So we just simplify this to -3 over x squared so that it's written with a positive exponent. Not a whole lot to do with that first one. What about this second one? Well, this is negative of 3x to the -2, or really we can think of this as like -1 times 3x all to the -2. But 3x all to the -2, that's either a product to a power that I could simplify that way, or I could use my negative exponent property. I can make this 1 over 3x to the second power. But this is -1 times 1 over, and 3x squared is 3 squared times x squared. -1 times 1 over 9x squared, or just -1 over 9x squared. Right. So my constant that was 3 in the numerator in the first expression turned into a 9 in the denominator in the second expression. The negative stuck around, the negative sign, and the x squared is still in the bottom. And then what about our third example here? -3x all to the -2 power. Well, here my whole parentheses is to the -2 power. So this is like 1 over -3x squared. Or this is like 1 over -3 squared, my numerical part, my numerical factor squared, times x squared. But -3 squared, -3 all squared, is 9x squared. So here I get the 9 that's in the denominator, like the green one, but that negative squared off, the negative turned into a positive. Be very careful when you're looking at strings of factors that are raised to a power, especially when there's only one power at the end. Be very careful about exactly what all is being raised to that power. Here it's just the x that's being raised to the power. Here it's the 3x that's being raised to the power. And here it's the entire -3x being raised to that power. Any questions so far? Okay, a little short diversion onto scientific notation. So I kind of did a little bit of a write-up here, but the basic idea of scientific notation is we can take a number like 351 and we can write it as a similar looking number times a power of 10. So like 35.1 times 10 to the first, or 3.51 times 10 to the second, or 0.351 times 10 to the third, or even 3,510 times 10 to the -1. We can take that decimal point, if we don't see it in a number like 351, it's implicit right at the end, and we can shift it left or right by multiplying by powers of 10. So we say that a number is written in scientific notation when the number is written as, and let me bump this down to the next line, as a times 10 to the k, where a is a number between 1 and 10. A is a single digit number. So we want exactly one digit to the left of the decimal point. So why would we want to do this? This seems like a lot of hassle. Well, one thing is if we're working with very large or very small numbers, or if the two numbers vary significantly in magnitude, this is really helpful. If you're looking at the mass of a proton or something, you don't want to write point a whole bunch of zeros and then some numbers. It's going to be really hard to tell how many zeros there are, to count them or anything like that. You'd much rather write, whatever, 3 times 10 to the -19 or something. I don't know if that's the right mass or not. And it lets us quickly determine the relative size of numbers that we can compare. If I have point a whole bunch of zeros and some numbers and point a whole bunch of zeros and some numbers for two numbers, a whole bunch of zeros plus or minus 1 0 is like 10 times as large, right? If you add a zero to your bank account or take a zero away from your bank account, so to speak, you'd be either very happy or very sad, depending on which direction that was, whether it was being appended on or taken away, right? Um, so it's much easier for me to look at a number like 3 times 10 to the 8th versus 3 times 10 to the 9th and see, oh, okay, one of them is 10 times as big as the other. If I had, a 3 with 8 zeros after it and a 3 with 9 zeros after it, it just kind of looks like 3 with a bunch of zeros after it. It's harder to tell what the relative size is. Okay, so let's write these following numbers in scientific notation. So here I have 351 with a decimal point implicitly at the end. I want to move that decimal point two places to the left to give me 3.51. So I have exactly one non-zero digit to the left of the decimal point. To move my decimal point 2 places to the left, well, that would have multiplied by 10 to the negative 2 to make that happen. So to undo that multiplication by 10 to the negative 2, I multiply by 10 squared. Right? 3.51 times 10 squared is 351. Or 14,375. 1, 2, 3, 4 decimal places to the left. And times 10 to the 4. Moving the decimal point 4 places to the left, basically multiply my original number times 10 to the minus 4. To undo that, to restore my original number, I need to multiply by 10 to the plus 4. 0.007. We move 3 places to the right. So this is just 7 times. Moving 3 places to the right is like multiplying by 10 to the plus 3. I need to multiply by 10 to the minus 3 to account for that, to fix that. Negative 37.41, the fact that it's a negative number doesn't change the process. We'll move the decimal point 1 place to the left. That procedure, moving it 1 decimal place to the left, is like multiplying by 10 to the negative 1. I need to multiply by 10 to the plus 1 to undo that. Or a negative point, a bunch of zeros, and then 3, 4. I have 1, 2, 3, 4. I need to move 4 places to the right. The negative just comes along for the ride. Moving 4 places to the right is like multiplying by 10 to the 4th. So I need to multiply by 10 to the negative 4 to undo that. Okay. So scientific notation, you've probably seen this in a science class or two, as well as, hopefully in a math class previously, but it's a pretty important idea. It's pretty useful. We don't use it a whole lot in math courses, but pretty useful in the sciences, though. We could go the other way as well. We could write the following numbers as decimals. We could take them out of scientific notation. This is particularly helpful if we're, say, looking to enter them into the calculator. A lot of times it might be easier to do operations with these in the calculator if they're not in scientific notation. So what about 7.21 times 10 squared? Well, we just think of this as a basic multiplication problem. Multiplying by 10 squared moves my decimal point 2 places to the right, 721. Or 7.21 times 10 to the negative 1. That 10 to the negative 1 moves my decimal point one place to the left, 0.721. 7.21 times 10 to the fourth. Well, here I want to move 4 places to the right, but I don't have enough places to move that far. That's okay, though. I can always append extra zeros on the rightmost end of my number to the right of the decimal point, or on the leftmost end of my number to the left of the decimal point. So 7.21 is the same as 7.2100. And now I have enough like buffer or padding that I can move over 4 decimal places. So this is 72100, so 72,100. And similarly, something like 3.09 times 10 to the negative third, I want to move 3 decimal places to the left, but I don't have enough places, but that is not a problem. I can always stick a couple of zeros to the leftmost end of my number onto the leftmost end of my number, as long as I'm to the left of the decimal point. And now I can move 3 places to the left, and this is 0.00309. Now, nicely enough, multiplying and dividing numbers in scientific notation is actually pretty easy. The reason is that scientific notation is inherently just the product of 2 things, and multiplication is commutative, and division works pretty nicely with multiplication. So if I want to add or subtract these, I put them in decimal form, add or subtract them, and then bring them back if I need to. But if I want to multiply or divide them, I can do that kind of in situ, so to speak. 6 times 1.5 is 9. So just multiplying these bits. 10 squared times 10 to the negative 3 is 10 to the negative 1, right? 10 to the 2 minus 3 power. And that's actually already in scientific notation. So that worked out pretty nicely. And 9 times 10 to the negative 5 over 6 times 10 to the negative 2. Well, that would be 9/6. Well, that's 1.5 times. And then I'd have 10 to the negative 5 over 10 to the negative 2, or that's 10 to the negative 5 minus a negative 2, or that's 10 to the negative 5 plus 2, 10 to the negative 3. So multiplication or division with numbers in scientific notation works pretty nicely. Okay, any questions on anything we did today? So our plan next time is to work through multiplying polynomials and continue on from there in chapter 5. I would recommend looking over some of this material because specifically with multiplying polynomials, this can be one of those things where there are some easy mistakes to make, and we don't want to make those errors if we can avoid it. So take a look over 5.3 before next week's lecture, and then we'll hit the ground running with multiplying polynomials next time. All right, I will end the recording.